Okay, guys, so what happened was this used to be an animation that I could have you guys do and work through and kind of read the stuff yourself and stop and ask questions and do whatever you needed to do. But it was a Flash program. And of course, Flash has gone away and they say they've replaced it with something else, but that's a lie. So, at any rate, somebody had the foresight to make a video of this. But they just video and click through and whatever. So, what I'm going to do is we're going to pretend like I'm the one clicking and we're just going to kind of read through this. So, I'm going to play the video and pause it, and it's just going to be a little bit awkward, but that's okay because you'll get the point. So, the first thing they're going to do is click on the tab that says flight dynamics. So we're going to take a look at what happens with flight dynamics. So you've got this nice diagram of a knife and you've got blood dripping down to the end of it. And then they've got a diagram showing you the surface tension and then gravity pulling down on that blood drop. So then it says that blood that's exposed from an open wound or present in sufficient volume on an object. So if you've got enough of it, such as the blood on this knife, will be pulled to the lowest point on its source surface. So that basically just says gravity is going to pull the blood down as low as it can. As the droplet increases in volume, so as the droplet gets bigger, the forces of gravity will eventually overcome the combination of the droplet's surface tension and its adhesive force to the object. So basically, there's a certain amount of tension that is blood staying connected to blood, and then there's a certain amount of tension that is blood staying connected to the knife itself. And at a certain point, the force of gravity is going to be stronger than the combo of blood wanting to stick to blood and blood wanting to stick to the knife. When that happens, it will pull the droplet away from the object's surface and towards the ground. This drop can also be affected by inertial forces as the weapon is swung. So basically, things that are just making the blood droplet change direction by the swinging of the weapon. But in the simplest scenario, gravity and surface tension play the greatest role. So now we're going to click next, and it's going to talk to us about a passive drop. So as gravity causes more and more blood to flow to the collection point, the opposing forces of surface tension and gravity, so surface tension holding the blood to the blood and gravity wanting to pull the blood away, those opposing forces will cause the blood to be retained in what is called a passive drop. Eventually, enough blood will have flowed into the passive drop. So the passive drop becomes almost like a container that's holding more and more and more blood. Enough blood will have flowed into it, that its weight will allow gravity to overcome the surface tension and pull the drop away from the object. So once enough blood gets in there, it's going to be heavy enough that gravity is going to win. And then this is cool. We're going to see this little drop. So as the blood droplet pulls away from the object, the surface tension of the droplet will cause the teardrop shape that it forms to retract back in towards the center of the droplet. This snapback force starts the droplet oscillating between spheroid and spheroid oblong. Definitely not phrases you need to know. As the droplet's surface tension evens out across its entire surface, the oscillation decays and the drop takes on a perfectly spherical shape. All that means is that as the droplet goes further and further down, the amount of the expand, contract, expand, contract, expand, contract is going to get smaller and smaller and smaller until you get to a perfect sphere. So let's watch that a couple times and watch how the droplet gets bigger, smaller, bigger, smaller, bigger, smaller. But each time it does, it's slightly less of a difference between the bigger and the smaller. So now we have some craziness where they're showing us just some information about the downward force and the force of friction. So a larger droplet experiences the same acceleration due to gravity, but due to its greater mass, this translates into a greater downward force. So it's going to be the same acceleration, but it's going to hit harder. Although the larger droplet does have a greater surface area than the smaller droplet, and therefore experiences more friction from the air, the volume has increased to an even greater scale. You don't need to know anything about that crazy formula. Therefore, even with its greater surface area, The larger droplet is still able to reach a higher speed than the smaller one before developing sufficient friction to counteract its downward force. Okay, so that's just some nerdy physics for those of you who are interested in it. Regardless of the surface onto which a blood droplet is falling, the angle or velocity at which it does so, or the volume of the droplet, there are 4 distinct phases involved in the reaction of a moving droplet with impact against a surface. Those are discussed here. So you can see that we have 2 different views here. We're going to be able to see what happens to this blood droplet from the side, and we're going to see what happens if we look at it with sort of a bird's eye looking down view. So phase 1 is contact and collapse. So upon initial contact with the surface, the droplet begins to collapse from the bottom upward. The collapse occurs at the portion of the droplet currently contacting the surface, while the portions above remain intact. As this collapse progresses, the displaced blood is pushed outward. In this case, it forms an outwardly advancing rim around the collapsing droplet. At acute angles, the rim forms on the side of the droplet opposite the angle of impact and is pushed in that direction. Phase 2 is displacement. Once the droplet has finished collapsing, most of the blood that has not yet been pushed into the rim is carried there by its remaining outward inertia. Slight dimples and spines begin to form on the edge of the pool based on irregularities on the impact surface. But so far, the surface tension of the blood has not been broken, and it still forms essentially a single mass, despite having undergone considerable changes in shape. Phase 3 is dispersion. Blood is forced into the boundary rim and into protrusions that rise upward. As the volume of blood in the rim and protrusions becomes unstable, inertia begins to separate the structures, resulting in the creation of satellite spatter. In the case of a droplet hitting a surface at 90 degrees, this takes the form of a crown or blossom effect. At more acute angles, a wave cast-off occurs on the side of the rim farthest from the angle of impact. Phase 4, retraction. Recall that as the force of the droplet's impact on the surface is trying to throw the mass of blood apart, the surface tension is still trying to hold it together as a single unit. In this phase, the surface tension finally overcomes the blood's waning momentum. The spines between the satellite spatters and the parent stay narrow as blood is drawn into one or the other. Satellite spatters that have enough momentum are able to break off completely in this phase, forming separate stains. So here we can watch it go all the way through all 4 phases. And now angle of impact. When a blood droplet strikes a surface from a 90-degree angle, the resulting stain will be basically circular. There will be no long or short axes, and the spines, scallops, and satellites will occur moderately evenly all the way around. Very little difference will be discernible between drops that impact anywhere between 90 degrees and 75 degrees. If we click on 70 degrees, though, and we change the angle, below 75 degrees, spines begin to become more prominent on the side of the spatter opposite the angle of impact. So this blood is coming in this way, and so our spines are more prominent on this side. So we can tell that the blood is moving this way because that force, that momentum, forced the spines out this way, forced the satellites out this way. If we change then to 60 degrees, we can see that we're going to have a slightly different angle, a slightly more elongated drop. So as the angle of impact gets lower and lower, generally between 75 degrees and 40 degrees, the elongation of the spatter stain becomes more and more apparent, and the spines, scallops, and satellites are focused more and more to the side opposite the angle of impact. Okay, so we have 45 degrees now, and they changed up the direction for us, and now they're going to move us to 25 degrees at highly acute angles, generally below 40 degrees. The nature of the outflow changes. A single satellite tends to form, acting essentially like a second spatter emanating from the first one, causing a distinctive exclamation point stage.